everyone. Welcome back to the lectures on Introduction to Multi-Agent System. In today's lecture, we'll continue our discussion on the properties of incidence matrices, especially the properties pertaining to the rank of an incidence matrix. So let's get started. Before we get started with the properties of the incidence matrix, let us first quickly look at some preliminary information which will be useful for us in proving the property. So let's get started. Follow the preliminary section. The first preliminary says that consider two matrices A and B. Then the rank of the product AB is given by, let's highlight it in a different color, rank AB is less than or equal to minimum of the rank of A and the rank of B. What does this imply? This implies that whenever we are taking a product of two matrices, what we can say with absolute certainty, something that follows from this fact, is that the rank of AB is less than or equal to rank of A. Similarly, rank of AB is also less than or equal to the rank of B. Meaning, when we are multiplying two matrices, the rank of the product is less than or equal to the ranks of the individual matrices which we are multiplying. This is the first preliminary. The second one says that consider an undirected graph G with vertex set denoted as V. Suppose V is equal to 1 to n, or let's write it as V1 to Vn. Let us consider a set of two vertices shown here. Suppose this is what G consists of, just two vertices. The number of vertices here is equal to 2. And how many edges do we need to add so that G becomes connected? The answer is just one edge. Meaning, the minimum number of edges that we need to add here is simply equal to 1. Let us add one more node to the network. Suppose this was G1, this was G2. Now, what can we do again? In order to make G2 connected, we need to add just one more node here. Meaning, if n is 2, now, if the cardinality of E is equal to 2, again, then G2 becomes connected. Similarly, let us add one more graph to the network, one more vertex to the network. Again, how many edges do we need to add so that the graph remains connected? The answer to that question is simply 1. Now that one node one edge, I can add here. I can add here, or we can have many other formulations as well. But we can also add it here in this manner. Either way, again, if the number of vertices is equal to 4, then M, or the minimum M, is simply n minus 1, which equals 3. We see that we could traverse this graph. Let's also keep adding the edge numbers. Sorry, the node numbers. Then we see that in each case, there are just 3 edges which are required to make this graph connected. Hence, to sum it up, we can say consider an undirected graph G with a vertex set V with cardinality of V being equal to n. Then the minimum number of edges that are required to make G connected is n minus 1. Just to see one more quick example, we can take a larger graph. Let us add an even larger graph. Let's write it 5, 6, 7, and 8. So currently, okay, let's simply add one more edge. Now, if we see the cardinality of the vertex set n is equal to 8, and the number of edges that we have is equal to 1, 2, 3, 4, 5, 6, and 7. So M here is equal to 7. Let us do something. Let us try deleting any one of the edges. Say this. If we delete it, we see that the network now has become disconnected, meaning we definitely need to have 7 edges so that the undirected graph with number of vertices being equal to 8 remains a connected graph. With this, we are now ready to discuss our next property. Before we move on, let me just highlight one more thing as a reminder. This is just a quick recap of a terminology. We can use the same graph for this. Let us consider the undirected graph shown here. We see that this graph here is actually a disconnected graph. This is disconnected. However, what we also observe is the graph actually has 2 components. This is the first component, and say this is our second component. and each component here is actually connected. Hence, we say that suppose this were our graph G, G is a disconnected graph which has two connected components. Now we are ready to discuss the property. So let's get started. This property pertains to the rank of the incidence matrix. So let's directly write it. Rank of an incidence matrix. We know that it's not necessarily a square matrix. Its dimension is n cross m. Okay, so how do we calculate its rank? And it goes this way. Consider an undirected graph G with n number of nodes and m number of vertices. Meaning, if we define G as V comma E, then M is equal to the cardinality of the edge set, N is equal to the cardinality of the vertex set. This is what is given to us. There's yet another information that we've been provided with. That is, let the number of connected components of G be N C C. The number of connected components. Just to quickly remind you, in the case that the graph is disconnected as shown here, we can break it into or consider it as the union of different components such that each of the component is actually connected. Hence, for the graph that is shown here, G has two connected components. So without loss of any generality, and to keep it very general, we are assuming that, let us say, it has some NCC number of components. Then the rank of the incidence matrix the incidence matrix is denoted as B n cross m is given by this. Rank of B is exactly equal to n minus the number of connected components, which is NCC. Meaning, we can just look at the graph, undirected graph which is given to us, see how many connected components it has. If the graph is connected, then the number of connected components is simply 1. If it is disconnected, then we know that there's more than one connected component. Just by using this information, without even constructing the incidence matrix, we can directly comment on its rank. So let's look at a proof of this result. The proof is actually quite straightforward. Without loss of any generality, we start by considering a connected graph. Later on, we will show that how the proof can actually be extended to an arbitrary graph with multiple connected components. But to begin with, let us consider a connected graph. Just because the graph is connected, there are several things now we can say. What are those things? Let us construct a connected graph so that we can easily see a few things. Now this graph is connected. Then we know that we can start at any vertex and reach any other vertex. So now we have constructed a connected graph. Okay, now let's keep it this way. So now what are the points that we can conclude just because the graph is connected? The first one is that the number of connected components NCC is obviously equal to 1 because the graph is connected. So as a whole, it is a connected graph. The second important thing that we can conclude is what can we say about the number of edges in the graph? So let's look at the graph a bit more closely. Let's number the vertices and 5. So n here is equal to 5. And what is the minimum number of edges that I need so that the graph is connected? That is equal to 5 minus 1 given by 4. Hence, we see that it has to have, as you can see, at least 4 edges. But obviously, if I now add one more edge, the graph still remains connected. Meaning, in general, what we can say with certainty is the number of edges in a connected graph. Let's write it here as we denote the connected graph as G. Connected graph G is, say, M. We can highlight it. M has to be greater than or equal to n minus 1. This is also something we can definitely say just because the graph is now connected. Okay, with this, let's move ahead with the proof. In general, we also know that the Laplacian L can be factored as B W times B transpose. What is W? So we covered it in the previous lecture. W is simply the matrix, a diagonal matrix where each diagonal entry is simply equal to the weights of the edges, meaning it has a rank, it has full rank and its dimension is equal to M cross M. Okay. And we know that the rank of B is N cross M and the rank of B transpose is equal to M cross N. In the previous topic, when we were studying the Laplacian matrices, we discussed there one more property for a Laplacian, which says that if G is connected, then the rank of Laplacian the Laplacian matrix L is equal to n minus 1 for a connected matrix. So what do we know here? We know that the rank of L is equal to n minus 1. We know that the rank of W is equal to M, exactly equal to M. So what are the conclusions that we can draw here? We know that let's write it. Since L is equal to BW transpose, we know from before, from the preliminary points that we discussed before, that rank of L is less than or equal to rank of B, which implies that rank of P, we know that the rank of L is n minus 1 because G is a connected graph. So rank of B, we can say quite directly that it is greater than or equal to n minus 1. Okay, so this is the first important point that we can say. We can say one more thing about the rank of P, that is, yet another property which holds for every Laplacian, every incidence matrix B with dimension n cross m is 1 n transpose B is equal to 0 m transpose. What does this mean? This means that this straightforwardly implies, let's write it. This implies directly that the rank of B is now less than or equal to n minus 1. So what do we have? We have two different things. First, we see that rank of P has to be greater than or equal to n minus 1. Secondly, we see that rank of P should be equal to less than or equal to n minus 1. When can these two properties simultaneously hold? When can these two inequalities simultaneously hold? So let's write this as a first inequality, 1, and this as a second inequality, 2. For the inequalities 1 and 2 to hold simultaneously, we must have rank of P as being exactly equal to n minus 1. So what did we start with? We started with a connected graph with n number of vertices. And we saw that the rank of V is directly equal to n minus 1. Now, let us consider this. Suppose this was a connected graph. And say this. Suppose this was a connected graph. We can have more vertices here. What holds for this is that, let's say this has n1 number of vertices. Then we know that the rank of the rank of the incidence matrix for this component is straightforwardly equal to n minus 1. Similarly, if we now construct yet another component, which has some n2 number of graphs, say this has some n2 number of graphs, then the corresponding rank of the incidence matrix for this component is n2 minus 1. We can do it quite similarly for every other connected component that is there in the undirected graph. Suppose this is what our graph looks like. And this is equal to some n, let's say n bar. Then this rank is equal to, so n bar is not a good notation. Let us say, we know that there are, suppose, ncc number of connected components. Then we know that this is the nccth component, or this has, say, nk number of nodes here. Then the incidence matrix has a rank of nk minus 1. Putting all of this together, the rank of the overall matrix would simply be given by the summation of n1 adding up to nk minus 1 keeps on getting added up, and the ncc number of times 1 will occur, so it is minus n, and all of the nodes put together is simply n minus ncc. This is the rank of the incidence matrix for a general case. The incidence matrix, much like the adjacency, degree, and accretion matrices, have quite nice properties, as we studied in the 3 lectures that we discussed on the incidence matrix. With this, we will conclude today's lecture, and in the lecture, we will move towards designing continuous time distributed algorithms to achieve consensus. We already know a discrete time rule which can give us consensus. Is there any continuous time rule which can give us consensus? The answer to that is yes, which is the Laplacian flow. So, in the next lecture, we'll look at the Laplacian flow. Thank you.